Okay, so let's get into finishing off the part of the lesson that I want to get done before we meet again on Thursday and Friday. And there are a couple of things that I want to talk about before I get into the example that I wanted you to work in class from last time. And I kind of wanted to talk about this first before I discuss what I'm going to talk about now. But the I think the best analogy I can give you in regards to visualizing what's taking place when finding area enclosed by a polar curve or area enclosed between two polar curves. I don't know if you guys have ever watched movies. I know they're in older movies, but when they have radar systems for airplanes or radar systems for military ships or submarines, and what the radar looks like is what I have drawn on the left. Like you've got a circle, and then you've got a radius extending from that circle. And then what happens is the radius is going to get spun around the circle. Okay, so after some time elapses, your radius is going to be over in here. And then after some more time elapses, your radius is going to be over in here. So if you picture that radius getting circled, what happens on a radar is if like um, airplanes or submarines or ships show up, you'll see a blip on the radar. So those two blips would be airplanes, for example. So as your radius swings around, continues swinging around, it'll pick up blips, and that lets you know where enemy airplanes or enemy submarines or enemy like ships are relative to your location. Okay, so I want to use that same idea for you to visualize what's happening whenever we are trying to calculate area enclosed by a polar curve. Because if you were to, for example, try to take the area formula where a is equal to 1/2 the integral from alpha to beta of r squared d theta, if you were to use that for that picture to the right, what would happen is you would extend a radius from the pole to where theta is equal to alpha, and then extend another radius from the pole to where theta is equal to beta. And then if your angles move here, you're taking a look at what portion of that curve gets swept out, and the portion of the curve that gets swept out is that portion right there. And that portion of the area is only enclosed by the graph r is equal to f of theta. Okay, so for some later examples, we're going to take a look at what happens when area is enclosed by two graphs. But the examples that we've done thus far, the area has been enclosed by one graph. So if we take the last example that we did in class for the cardioid, I think our setup for that, we got area was 1/2, and then we multiplied it by 2 times the integral from 0 to pi, because our graph had symmetry. So it was 1/2 times 2 times the integral from 0 to pi of, I think our function was 4 plus 4 times the cosine of theta, which we squared and integrated with respect to theta. So if you picture what's happening here, you're starting with the radius over here at theta is equal to 0, and then you're just sweeping out until we get to theta is equal to pi, which happens right here. Okay, so when we sweep out from 0 to pi, this integral is calculating all of this area here, and then when we multiply it by 2, that's what's going to be what doubles that area, which gives us the entire area here in purple. Okay, so I want you to have that visual of if we had the radar there, what is getting swept out by that radius. Okay, and that's going to help you like visualize what's taking place whenever you find area between a polar curve. Okay, so let's go to the example that we left off with here. So we were asked to determine the area of the inner loop of r is equal to 2 plus 4 times the cosine of theta. Okay, and what we said in class was we had to set that radius equal to 0 to figure out when the graph hits the pole. And we'll talk about the significance of that in a second. So we get 2 plus 4 times the cosine of theta is equal to 0. And then when we solve for cosine, we get the cosine of theta is going to wind up becoming negative 1/2. So if we want to calculate where cosine is negative 1/2, we know cosine is going to be 1/2 at the reference angle pi over 3. And then we know cosine is negative in quadrants 2 and 3. So the angle in quadrant 2 with reference angle pi over 3 is 2 pi over 3. And in quadrant 4, it is 4 pi over 3. Okay, so those angles are going to be really important for us whenever we set up our integral here. Now, why do we have to calculate when our graph hits the pole? Well, if we were to follow our graph here, our graph would start over here at theta is equal to 0. And then our graph would travel along this curve until it hits the pole here. And when it hits the pole here, that's what starts the inner loop. Okay, so that's what starts the inner loop. And then when it hits the pole again, that's what ends the inner loop. Okay, and then our particle would travel along the curve like this. Okay, so why does this curve here have an inner loop? Well, the reason this curve has an inner loop is if we pick values between theta is equal to 0 and theta is equal to 2 pi over 3, our r values are greater than 0 on that interval. So once we set those bearings, if our r value is positive, our graph is moving forward along those bearings. But between the theta values of theta is equal to 2 pi over 3 and theta is equal to 4 pi over 3, if you plug values between 2 pi over 3 and 4 pi over 3 into that equation for r, you're going to wind up getting r values that are negative. So when you set the bearing, so I'm going to go ahead and like dash this in really quick. If I set the bearing here at 2 pi over 3 and the bearing here at 4 pi over 3, so for all the angles in between these two angles, our r value is negative, so our graph has to travel backwards for those bearings, which is going to put like the graph over here in green. So on those bearings, if the r value is negative, the graph is traveling backwards, which puts the inner loop like inside of that curve. Okay, so what we're trying to do here is we are trying to calculate the area of that inner loop. Okay, so if we want to calculate the area of that inner loop will be 1/2 times the integral from 2 pi over 3 to 4 pi over 3 of r squared, so that's 2 plus 4 times the cosine of theta squared, which we're integrating with respect to theta. But when we look here, so I'm going to draw this in black, that graph is symmetric with respect to the x-axis, okay? So what I can do instead is I can rewrite this formula as the area here would be 1/2 times 2. Now you have the option here of integrating from 2 pi over 3 to pi, okay? Because again, it's symmetric with respect to the x-axis, so we can write the integral as 2 pi over 3 to pi. Or the other way that we can write this, and this is how I'm going to do the problem, is I'm going to integrate from pi to 4 pi over 3. Because when I integrate from pi to 4 pi over 3, that's going to calculate like the top half of that area in green. And then when I double it, that's going to give me the entire area in green. Okay, So we're going to integrate 1/2 times 2 times the integral from pi to 4 pi over 3 of 2 plus 4, times the cosine of theta squared with respect to theta. Okay, and this is going to be the function here that I integrate. Again, if you have the opportunity to use symmetry, do so, because this is going to be harder. Like when we take the antiderivative, it's going to be harder to evaluate it at two angles with reference angle pi over 3 than it will with a single angle with reference angle pi over 3 and a quadrantal angle. If you have the opportunity to evaluate your antiderivatives at quadrantal angles, you want to do so. It's going to make the calculation, it's going to make the numbers in the calculation much easier for you guys to work with. Okay, so let's go ahead and expand this. So area here will be equal to 1/2 times 2 is 1. So we have the integral from pi to 4 pi over 3. I'm going to FOIL out 2 plus 4 times the cosine of theta squared. So that's going to become 4 plus 2 times 4 times 2 is going to be 16 cosine of theta, plus 4 cosine of theta squared is going to be 16 cosine squared of theta d theta. And then this term here is problematic for me, so I'm going to use the power reducing formula to rewrite that. Okay, so area here will be the integral from pi to 4 pi over 3 of 4 plus 16 cosine of theta. I'm going to pull 16 out front, and then I can rewrite cosine squared as 1/2 times the quantity 1 plus the cosine of 2 theta. And then I'm going to combine a couple of steps here. Okay, so I'm going to multiply 16 times 1/2, which gives me 8. And then I'm going to distribute that across both of these terms. And then I'm going to combine the constant terms. Okay, so we get a equal to the integral from pi to 4 pi over 3. So 16 times 1/2 is 8. 8 times 1 is 8. 8 plus 4 is 12. Plus 16 cosine of theta. When I distribute 8 across the next term, we get plus 8 times the cosine of 2 theta. And then we are integrating that with respect to theta. Okay, so let's go ahead and take the antiderivative here. So a is going to be equal to the integral of 12 is 12 theta, plus the integral of 16 cosine of theta is going to be 16 times the sine of theta, plus the integral of 8 times the cosine of 2 theta will be 8 sine of 2 theta divided by 2, which is going to become 4 times the sine of 2 theta. And then we're going to evaluate that at 4 pi over 3 and at pi. Okay, so when we plug in 4 pi over 3, 12 times 4 pi over 3 will wind up becoming 12 times 4 is 48 divided by 3, so that's 16 pi, plus 16 times the sine of 4 pi over 3. That's going to be 16. The sine of 4 pi over 3 is going to be negative rad 3 over 2. So 16 times negative rad 3 over 2 is minus 8 rad 3. And then when I plug 4 pi over 3 into the last term, we're going to get 4 times the sine of 8 pi over 3, which 8 pi over 3, if I find an angle between 0 and 2 pi that is coterminal, that's going to be this 4 times the sine of 2 pi over 3. And we know the sine of 2 pi over 3 is rad 3 over 2. So 4 times rad 3 over 2 is 2 rad 3. Minus, so again, that was kind of complicated to evaluate. We'll see how much easier it is to evaluate with a quadrantal angle. So when we plug pi in, we get 12 pi plus 16 times the sine of pi is 0, plus 4 times the sine of 2 pi. The sine of 2 pi is also 0. So it's much easier to evaluate when we have quadrantal angles. That's why utilizing symmetry is so important. Okay, so the last thing for me to do is combine like terms. So 16 pi and 12 pi. 16 pi minus 12 pi make 4 pi. And negative 8 rad 3 plus 2 rad 3 is minus 6 rad 3. Okay, so that gives us the area of that inner loop. Again, if you can use symmetry, use symmetry. It makes the calculations way easier, way faster. Because again, imagine if you had to plug like 2 pi over 3 in the place of pi, that computation is going to be more convoluted. It's more complicated. Okay, so again, use symmetry when you have the opportunity to. Okay, so those are our examples of area enclosed by a single curve. Let's make things a little bit more complicated now. We want to find the area enclosed by two polar curves. Okay, so let's say we have are looking at this curve between the angles of theta is equal to alpha and theta is equal to beta. And then our two curves are r sub 1, which is equal to f of theta, and r sub 2, which is equal to g of theta. Okay, so the area that we are trying to calculate is the area in black. Okay, so I'm going to erase that area in black just for a second. Okay, so how do we know this area is enclosed by two curves? And the reason that we know this, okay, so I want you guys to pay attention to the graph really quick. Okay, I'm going to draw this, or let's go ahead and highlight this. Okay, so I'm going to highlight this first radius here in yellow. And I'm going to highlight the second radius up here in the light blue color. Okay, so if I were to take, again, picture the radar, okay, the analogy that I gave you with the radar, okay? So if I were to use that radar to sweep the radius from the radius in yellow to the radius in blue, again, I'm going to draw arrows to like sweep this out. Okay, so it's being swept out like this. When we look at like all of the radius or all of the radii in between, okay, so if I take this radius in between, this purple one here, or this green one here, you see how those two radii are going to hit both of those curves? So it hits this green curve here, the smaller curve, and it also hits this polar curve in red, which is the bigger curve. Okay, so if we're trying to calculate the area, that area is enclosed by the two polar curves. Okay, so very simply, all we have to do is, if we're trying to calculate the area between the two polar curves, is if I take the area of the bigger polar curve, okay, so let's go ahead and do this in red. So if I take the area of the bigger polar curve, the area of the bigger polar curve will be 1/2 times the integral from alpha to beta of my longer radius, which is r sub 1 squared d theta. Okay, so let me go ahead and go back to this graph. I'm going to erase this stuff. Okay, so the area of the bigger polar curve is going to calculate all of this area here in red. Okay, now again, if we were trying to find the area in black, what we want to do from that area in red is we want to take away the area in green, which would be this area right here. Okay, so we're going to subtract the area in green. So the area in green would be 1/2 times the integral from alpha to beta. The area in green, we would integrate r sub 2 squared with respect to theta. And if you combine those two statements into a single statement, then area here would be 1/2 times the integral from alpha to beta of the longer radius, so that's r sub 1 squared, minus the shorter radius, r sub 2 squared, which we're integrating with respect to theta. Okay, so that right there is how we find the area enclosed by two polar curves. Okay, so when we take that area that we found in red minus the area that we found in green, that gives us this leftover area here in black. Okay, so let's use that to do this one. And this is going to be the last example of finding area between polar curves that I'm going to work out by hand. Okay, the rest of these we're just going to set up only. Okay, because I think, like, given what we've done by hand, and this is just kind of like utilizing what we learned in chapter 7, you should be able to integrate this by hand. So this will be the last thing that we actually work through the value of the integral by hand. The rest of them we're just going to set up the integrals for only. Okay, so here's what the example asks. It asks us to determine the area that lies inside r is equal to 3 plus 2 times the sine of theta, and outside r is equal to 2. Okay, so again, determine the area that lies inside. R is equal to 3 plus 2 times the sine of theta, and outside r is equal to 2. Okay, so here's what I want. I want you guys to plug these into your calculator. Okay, give yourself a good viewing window, and then graph both of these in your notebook, and then we'll talk about like how we proceed from there. Okay, so go ahead and pause the video to do that. When you're done, go ahead and unpause, and then we'll go over it together. Okay, so I'm going to go ahead and graph this. So the graph of r is equal to 2. That's going to be a circle centered at the origin with radius 2. Okay, so I'm drawing that in red. And then I'm going to draw the graph of 3 plus 2 times the sine of theta in green. So graphically, that's going to look like this. It's going to pass through these points at negative 3, 0, and 3, 0, and also pass through the point at 0, 5. Okay, so graphically, your function looks like that. So you guys played any like Mario Brothers or Mario Kart? It kind of looks like Toad, if like the hat is green and the face is red. Okay, so the area that we are trying to calculate is the area that lies inside the curve in green, but outside the curve in red. Okay, which is, I'm going to go ahead and shade this in black. Okay, it's going to be that area right there. Okay, so let's think about what we need to calculate here. Okay, so we're going to need to know what our limits of integration are going to be. And the limits of integration are going to occur where those two graphs intersect. So if we want to calculate the intersection point of those two graphs, we're trying to calculate where those two equations are equal to one another. So we're going to find where 3 plus 2 times the sine of theta is equal to 2. Okay, so we want to isolate sine, so I can subtract 3 and divide both sides by 2, and that's going to occur where sine is equal to negative 1/2. So sine is going to be equal to negative 1/2. Our reference angle, so sine is 1/2 at pi over 6. We know sine is negative in quadrants 3 and 4. So the angle in quadrant 3 with reference angle pi over 6 is 7 pi over 6, and in quadrant 4 it is 11 pi over 6. Okay, so again, we can tell that this area here is enclosed by two curves. Okay, so here's what I would guess. If I were to ask you guys to set up an integral to calculate this, I would guess the majority of you would do this. So you would do 1/2. Don't write this down, by the way, because it's incorrect. Okay, you would do 1/2 times the integral from 7 pi over 6 to 11 pi over 6 of the longer radius. I'm not going to write this part in yet. So it would be the longer radius, which is r sub 1 squared, minus the shorter radius, r sub 2 squared. And then you would integrate that with respect to theta. Okay, let's talk about what's incorrect with this. Okay, so if you took the integral from 7 pi over 6 to 11 pi over 6. Okay, so 7 pi over 6, I'm going to go ahead and highlight that in blue. 11 pi over 6, that angle would look like that. Okay, so again, picture the radar. If you take the integral from 7 pi over 6 to 11 pi over 6, that would sweep out all of this stuff right here. And that's not the area that we are trying to sweep out. What we're trying to do instead is we're trying to sweep out the area from here all the way around to here. So we have a problem with our limits of integration the way that they are written right now. So I want you to take a few seconds, think about how you can work your way around that problem. So how can we change our limits of integration so that the correct area is swept out? And the way that we can do that is if instead of writing this angle here as 11 pi over 6, if we wrote it instead as negative pi over 6, so if we integrate from negative pi over 6 to 7 pi over 6, then the correct area is being swept out, because that's going to sweep out like all of the stuff that I have highlighted in yellow. Okay, so you have to be smart to make sure that your limits of integration like are sweeping out the correct portion of the area. Now, when we look at this graph here, we see that the graph has symmetry with respect to that highlighted line in green. So what I can do with this, just to make the calculation easier for myself, is I can find the area by taking 1/2 times 2, okay, times, we can either integrate from negative pi over 6 to pi over 2, or what I'm going to do, I'm going to integrate from pi over 2 to 7 pi over 6. Okay, so what I'm doing is I'm calculating like all of this area here in blue. Okay, that's what my integral, just the integral. So if I were to get rid of this, if I were to get rid of that factor of 2, the integral from pi over 2 to 7 pi over 6, that's calculating the area in blue. And then when I double that, that's going to give me the entire integral in black. Okay, so we're doubling that using symmetry. Okay, so our longer radius is basically the distance from the pole to the curve that's the furthest away. Okay, and the curve that's the furthest away is going to be 3 plus 2 times the sine of theta. Okay, so that right there is our longer radius squared minus our shorter radius. So again, if you were to like, I don't want to draw because there's so much stuff on the graph here, but the shorter radius is the distance from the pole to the closest curve. And the distance from the pole to the closest curve is just the function value, okay, which in this case is 2. And then we have to square that radius as well. And then we are integrating this result with respect to theta. Okay, so again, these integrals are going to get like more and more complicated depending on what your curves look like. Okay, so this will again be the last one that we work through by hand. So 1/2 times 2, that's going to be 1. So I'm just going to get rid of that. Then we have the integral from pi over 2 to 7 pi over 6. I'm going to expand out 3 plus 2 sine of theta squared. So that's going to be 9 plus 12 times the sine of theta plus 4 sine squared of theta minus 2 squared is 4. Whoops, make that a parenthesis, which we're integrating with respect to theta. Okay, so area here is going to be the integral from pi over 2 to 7 pi over 6. I'm going to simplify. So 9 minus 4 is going to be 5 plus 12 times the sine of theta plus 4. And then we're going to, again, because we can't integrate this the way that it's written right now, we're going to use the power reducing formula to rewrite sine squared as 1/2 times 1 minus the cosine of 2 theta. Now, if you guys want, like, you don't have to write out this step. Like, if you just want to multiply 4 times 1/2 and get 2, and then multiply 2 times 1 minus the cosine of 2 theta, that's fine. Okay? All right, so I'm going to combine a couple of things in one here. So I'm going to go ahead and combine the constant terms. So the area here is going to be the integral from pi over 2 to 7 pi over 6. So 4 times 1/2 is 2. When I multiply 2 times 1, that's 2. 2 plus 5, so that's going to be 7 plus 12 sine of theta minus 2 times the cosine of 2 theta, which we're integrating with respect to theta. And now we have this written where we can integrate term by term. So a here is going to be the antiderivative of 7, which is 7 theta. The antiderivative of 12 times the sine of theta is going to be minus 12 cosine of theta, minus the integral of 2 times the cosine of 2 theta will be 2 sine of 2 theta divided by 2, which is going to become just the sine of 2 theta. And we're going to evaluate that at 7 pi over 6 and at pi over 2. Okay, so we're going to just go ahead and plug those values in again. And again, using symmetry is going to make the calculation easier because it's going to be easier for me to evaluate this antiderivative at pi over 2 than it would be at negative pi over 6. Okay, so let's plug 7 pi over 6 in first. So 7 times 7 pi over 6 is 49 pi over 6 minus 12 times the cosine of pi over 6, or sorry, the cosine of 7 pi over 6. So the cosine of 7 pi over 6 is negative rad 3 over 2. So negative rad 3 over 2 times 12 would be positive 6 rad 2. Minus the sine of 2 times 7 pi over 6 would be the sine of 7 pi over 3, which if I find an angle that is coterminal, that would be the sine of pi over 3. And the sine of pi over 3 is rad 3 over 2. Okay, minus, and then we're going to evaluate this at pi over 2. Okay, so 7 times pi over 2 is 7 pi over 2. Minus 12 times the cosine of pi over 2. The cosine of pi over 2 is 0. Minus the sine of 2 pi over 2, which is the sine of pi, which is also 0. Okay, so we need to simplify here. So my common denominator of these two is going to be 6. So A here would be equal to 49 pi over 6 minus, so 21 pi over 6. And then we get plus 6 rad 2, which is 12 rad 2 over 2. I'm sorry. That shouldn't be rad 2. That should be rad 3. This should be rad 3. I probably said it and wrote it down wrong. So that should be 6 rad 3. So it should be 12 rad 3 over 2 minus rad 3 over 2. So when we add and subtract the like parts, we get a here equal to 28 pi over 6 plus 11 rad 3 over 2. And 28 and 6 are both divisible by 2. So that's going to make a equal to 14 pi over 3 plus 11 rad 3 over 2. All right. So that right there is your area for that example. Okay. So last example I'm going to work on today asks us to set up an integral that calculates the area of the region outside r is equal to 3 plus 2 times the sine of theta, and inside r is equal to 2. So we have the same two polar curves as the previous example, but this time we are calculating a different area. Okay, so this time it's going to be the area outside of the green curve and inside of the red curve. Okay, so I want you guys to set up this integral and then pause the video, and then we'll talk about it for you to check your work. Okay, so let's see how we did here. Again, we need the same intersection points that we found in the previous problem. So the intersection points are r is equal to 7 pi over... I'm not going to recalculate that because we did that. Or sorry, that's theta. So theta is equal to 7 pi over 6 and theta is equal to 11 pi over 6. I'm not recalculating that. We did that in the previous part. Okay, so if we want to find the area in black, if we were to integrate from 7 pi over 6 to 11 pi over 6, that in fact does sweep out the correct area. Okay, so our area here would be equal to 1/2 times the integral from 7 pi over 6 to 11 pi over 6. The longer radius, so the curve that's furthest away from the pole here, is going to be 2 squared minus the shorter radius, the curve that's closest to the pole, would be 3 plus 2 sine of theta squared. And then we are integrating that with respect to theta. But again, I would not set it up this way. Okay, I would use symmetry, and the fact that we are symmetric with respect to the negative y-axis here means that you could either, so I'll go ahead and write it out both ways. You can set it up as 1/2 times 2 times the integral from 7 pi over 6 to 3 pi over 2 of that same function, or you can write it as 1/2 times 2 times the integral from 3 pi over 2 to 11 pi over 6 of that same function. Okay, so you have 3 different ways that you could set up the integral to calculate that area. Okay, and if that makes sense, you guys should be in good shape for the additional examples that we're going to discuss on Thursday and Friday. Okay, so that's it. That puts us in good shape. I should be able to finish that lesson on Thursday and Friday. If not, I may have like one more example to do on a YouTube video. Okay, so that's it. We'll see you guys on Thursday or Friday. Take care.